Good morning, everyone, and thank you for the opportunity to present my research today. My name is Suriya Dev Saravanakumar, and this project is titled Investigating Alzheimer's Disease Through Eye Movement Behavior Using Public Data. I completed this as part of my YRI Fellowship under the mentorship of Dr. Shweta MP and Dr. Shubham Kumar Jalan. This project focuses on whether eye tracking data, even when simulated, can support early detection of Alzheimer's disease using reproducible machine learning methods. Background. Why eye tracking? Alzheimer's disease impacts attention, memory, and visual processing long before symptoms even occur. One of the earliest changes occurs in eye movement behavior because eye movements reflect cognitive load. Some studies have shown that individuals with Alzheimer's tend to fixate longer, make shorter and fewer saccades, and blink more frequently. What makes eye tracking more exciting is that it's non-invasive, affordable, and scalable, especially compared to the expensive MRI or PET scans. So the core idea behind the project is, can we use changes in eye behavior as an early indicator of cognitive decline? Research overview. So the goal of my research was to test whether eye movement behavior alone can distinguish Alzheimer's patients from healthy controls. Since research since real clinical eye tracking data can be difficult to obtain, I created a synthetic dataset modeled on published medical literature. This dataset simulates fixation patterns, saccade amplitudes, and blink behaviors for both the groups. I then processed these features using machine learning models to see how well they could classify Alzheimer's versus the normal control participants. Overall, this work serves as a proof of concept that even simulated oculomotor data contains meaningful cognitive signals worth exploring for diagnostic use. So the methodology. So first of all, to build the dataset, I simulated 60 participants, 30 Alzheimer's versus 30 controls, using parameter values reported in clinical studies. So the fixation duration was modeled with a normal distribution, Alzheimer's at around 350 milliseconds and control around 250 milliseconds. Saccade amplitude was also normally distributed, smaller in Alzheimer's at around 2.5 degrees and 3.5 degrees for control. Blink rates followed a Poisson model, with Alzheimer's blinking more frequently. These parameters help me create a realistic eye movement behavior. After generating the data, I standardized all features for equal scaling, cleaned the data set, and used a tenfold cross-validation to test all the reliability. And, and in total, I implemented three models in R script: random forest, gradient boosting, and a feed-forward artificial neural network. And finally, I evaluated them using ROC AUC, PR AUC, F1 score, and accuracy. So first, I verified whether synthetic data reproduced expected behavioral differences. The results show exactly what we would predict from clinical literature. Alzheimer's participants had longer fixations, shorter saccades, and of course, higher blink rates. These all reflect slower, less exploratory gaze behavior. The gaze density heat map also shows tighter clustering for Alzheimer's, meaning they explore the visual space less. Next, I checked whether the gaze features were independent. The correlation heat map shows that all features, horizontal and vertical gaze coordinates, blink count, and frame index, had the correlations below zero point 0.2. This independence is important because it means that each feature contributes to unique diagnostic information, reducing redundancy and improving model robustness. So here's the model performance. The synthetic data. So I then evaluated how the models could classify Alzheimer's versus controls. The the random forest and ensemble models perform the strongest with the ROC of about 0.75, meaning that these models could rank Alzheimer's versus cases around 75% of the time, even though accuracy stayed 50%, which is expected with threshold classifications. Oh wait, excuse me. Yeah, sorry. I, I accidentally forgot to switch the slides, so I was actually finished talking about results and I was about model performance. Should I restart or should I just start from the results? Oh, oh, okay, okay. So the model performance. I then evaluated how well the models could classify Alzheimer's versus controls. So the RF forest and ensemble models perform the strongest with the AUC of about 0.75. This means that models could correctly rank Alzheimer's versus healthy cases about around 75% of the time just by using simple eye movement features. Even though accuracy stayed around 50%, which is expected with these threshold-based classifications, the high AUC shows meaningful and valuable discrimination. These results demonstrate proof of concept feasibility that even simulated data contains enough signal for AI to detect the cognitive differences. So, the gradient boosting machine, also known as GBM, next to understanding which features matter the most, I looked at the gradient boosting machine feature independence. The strongest predictors were the horizontal gaze coordinates, LX and RX. This is actually very consistent with neuroscience, especially since the horizontal saccadic controls tend to decline earlier in Alzheimer's due to changes in frontal and parietal network. Vertical gaze and blink rate also contributed meaningfully and in a diagnostic insight that which made it the reinforcing the multiple aspects of eye behavior reflect these cognitive loads. So this is the artificial neural network. I built the feed-forward neural network with five input neurons representing the gaze features, five hidden neurons, and one output neuron for classification. The ANN learned that nonlinear relationships in the data. Again, with similar results with the GBM, the horizontal gaze features produce the strongest activation rates and had the highest accuracy. Blink rate showed moderate influence, which reflects the increased cognitive fatigue. Overall, the ANN confirms the same pattern as the GBM. Eye movement dynamics alone carry meaningful diagnostic insights for Alzheimer's. Discussion. The simulated data successfully reproduced real Alzheimer's eye movement patterns, confirming the validity of the statistically modeling approach. The machine learning models perform consistently with AUC values between 0.55 and 0.76 and an F1 score of 0.67. These are strong results, considering the data is fully and completely synthetic. Across all models, the horizontal gaze behavior emerged as the most informative predictor. This mirrors well-established clinical observations of reduced saccadic range in Alzheimer's patients. The main conclusion from the discussion is that eye tracking has genuine potential and scalable as a non-invasive biomarker, especially for cognitive screening. So conclusion and future work. So concluding my research, this study demonstrates that eye tracking features such as fixation duration, saccade amplitude, and blink behavior can reliably distinguish Alzheimer's patterns from healthy controls, even when using simulated datasets. The approach is simple, reproducible, non-invasive, and low cost, making a promising direction for clients for early screening. For future work, the next step is to validate these models using a real patient and clinical data sets to assess the accuracy of with patients. I also plan to integrate additional modalities such as speech feature and EEG, which have shown strong potential when combined with gaze behavior. So long term, this research could contribute towards tools capable of tracking Alzheimer's changing over time and supporting early detection of Alzheimer's. So thank you. I'd like to especially thank my mentors, Dr. Shweta MP, Dr. Shubham Kumar Jalan, and the overall YRI Fellowship for their amazing guidance and support.